Hello, I'm going to try to show you how to use the JMT Texas Ditches with Shear calculation spreadsheet that we've developed to help us with our ditch calculations. So I'm going to start. This is one that is mostly filled in, so I'm going to start from a new ditch profile. So I'm going to do a save as on this file. And here I have the ditch profiles we have for the State Loop 335 project. I've already done the one for the frontage road southwest left ditches. So I'm going to try to walk through an example for the frontage road southwest right ditches. So I'm going to just go ahead and do a save as. I'm going to change the name of this into the spreadsheet to the ditch I'm looking at, which will be the frontage road southwest right ditch. And I'm going to check this one in. Okay. We're going to start with what we usually develop for our ditches to get the ditches drawn in the open roads model. We usually have a ditch profile. So I'm going to open that up. Frontage road southwest right ditches. And this was just generated using the print profile option in coordinate geometry in GeoPack. So from here in our spreadsheet, there is a raw data tab. And so in this raw data tab, you'll see that it has a place to copy in the raw data ditch output. So I'm going to delete the old output that is in this spreadsheet. And then I'm going to open up this notepad file for the ditches I am looking at. And I'm just going to copy it and paste it in there. Okay. And the next step is going to be to take this data and do what this says to do, to make it text to columns, eliminate and delete empty rows, and replace all the plus symbols with nothing, basically, that converts it to a number, and then format it to this custom number format, and that will show the plus sign, but it'll allow what's in the cell to still act like it's a regular number. So I am going to copy what I'm going to do, since I don't want to mess up this data by having to delete the empty rows. I'm going to copy it again down here and go through those steps. So the first was to go text to columns. So I'm just going to go data, text to columns. I want to do delimited. I want to separate anything with a tab, space, or a comma into a column. I'm going to say next, and then I'm going to say finish. So what we're really trying to get out of the GeoPack profiles is the station and elevation of every VPI in the ditch. This will help us to analyze the ditch in our spreadsheet, because it'll show the slopes of each segment of ditch, and then we're going to just put some basic geometry in there and run through the calculations. So I'll walk you through these steps. First, we're going to just clean this up a little. Let's delete all these rows with nothing on them. I'm just holding the control key down and hitting the left number on each row that is not needed. skipping the ones with actual VPI data for our ditches. Sorry, this is a bit tedious, but you'll see that it's better than the alternative. I think we can go ahead and do that. Keeping control held down so I don't lose everything. Okay, now I'm going to right click and hit delete. And that's going to clean that up a little bit. The next thing will be to do a control F, do a replace, and replace any plus sign, because that makes it a text cell. And I want to replace that with nothing. I'm going to say replace all. And then that many replacements. Now, since this is hard to look at and check against a ditch profile, which is in station format, I'm going to put the plus sign back, but through formatting. So I'm going to go format cells, custom, and the type I want to enter is number sign, plus number sign, dot 00. What that is doing and is making a plus and then the station for the last two digits, so the tens digits and the one digit. I'm not sure if you say that correctly, and then the decimals. So that's formatting it like a station would be formatted. You got to be careful not to select, because I did this on another one and messed it up, not to select this one. This one would make it, actually this one. I don't know, but I saw it messed up in some way. I'm not sure. I hadn't seen that issue before, but I saw it messed up. So this is how I've been doing it. Number sign, plus number sign, dot 00. And you'll see that's what we mean by that. Station 2418 plus 71.74. That's correct. So we want that format. Let's see if we did all the right steps here. Change the formatting, so that's great. I'm going to take these and take this data, move it back up here where it's more, it's going to be obvious when you open the spreadsheet. Or it's going to be readily visible and you don't have to scroll down to it. Okay, so there's that data in a very easy to use format. It's got every VPI and every elevation of your ditch flow line. That is going to be put in here. First, I'm going to try to walk you through how this spreadsheet is set up. And then we'll show you, and then we'll come back over and copy it in. So all the calculations are done on this tab here. And what it is doing is taking, based on your upstream ditch station and your downstream ditch station, it is looking up the geometry of the ditch from this tab based on those stations. So in each one of these, so it's looking up the upstream ditch flow line based on the upstream ditch station here, looking up the downstream ditch flow line based on the downstream station. It's calculating the ditch length based on the difference in stations. It's calculating the hydraulic radius based on the area over the wetted perimeter. It's calculating the area. You can dig into what all these are referencing, but it's set up to read everything that is on this ditch geometry. So I'm going to take our raw data. Right now I'm going to delete all this out. All this ditch profile geometry. I'm going to leave the sequence, and I'm going to leave this information. So this is a ditch row count, and this is used to help this tab pull the correct data. As if you see, this is looking up. We have a ditch row count here that it is pulling from. So it's pulling from this sequence to this sequence. This is the same as the ditch row count. I should let me rename that to be more clear. Okay, it's a little bit tricky how this works, but it's once you figure it out, it does the work for you. But I'm going to try to explain, show you how it's set up here. So these are set up with a VLOOKUP. It's looking at the ditch row count here, and that's for the upstream ditch station, and then the downstream, it's getting all the data from this row count here to read that station. Then everything else is looking up off of these stations. And as far as let me get the data over. We'll come back to that. Okay, so we're gonna drop in all these stations here. I'm just gonna paste the values. This is actually the Cornish Road, southwest into the right ditch now. Get the flow lines. Okay. Now you see these colors. These are left in there from the last one. I'm just going to get rid of the color scheme. But I recommend doing some kind of color scheme manually once we look at the data to help visualize it. So this row column C here tells us if the ditch is going down, as in as the ditch increases in station, the ditch is going down, or if it's going up, if the ditch is increasing in station and the ditch profile is going up. And that will recommend the sequence here for analyzing that ditch, because if it's going up, this sequence is going to be backwards looking, because this is the upstream. It's going to take 7.7 and then go to 0.6 because it's going up. So it's going to go from that one to that one. And at sometimes your ditch is going to go down, 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 then up, 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 down. So up, up. So we got to look when it says true. This is true if it's a high point. Otherwise, it's false. I'm going to go through and highlight all the high points we got. Because from the high point, you have to analyze the ditch going both ways. You basically have a ditch going one way, starting at the high point, and then you have a ditch going the other way. So it's upstream. The high point is upstream for two different ditch segments. So all of these true. And that's basically the end of our data. So let's highlight these and give this color. And the other segments, I'm going to give just a color to help us visualize. Okay, the ditch is going down, 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 down. This would be a low point, and it starts going up, 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 up. So we're going to make it go between two other colors. Let's go blue, and then green if it's going up. Green, it's going up. And I missed a high point here. Blue, it's going down. Green, it's going up. And we have a high point. And then we got blue going back down. I'm probably going to modify this to have some conditional formatting to take this step out. But I haven't gotten that far yet. So blue, it's going down. Green is going up. Down, down, down. Good. I like these long stretches. Okay, we're done. Okay, took a little break there. So we got these set up, and if you notice, when it's going down, it's saying to go from 1 to 2. So that's saying 1 would be the upstream station. So it would be this higher one, and then 2 would be the downstream station. And then when it starts going back up, it's saying it's going the opposite way. It's going from 6 to 5. And then when we get to these high points, it goes both ways. So because it's going up here, and so it's going 8 to 7, which is here to here. So it's analyzing from the 650.017 to where it's going down there. And then it's analyzing from 8 to 9 as well, because it's going back the other way. So this does the work for you so that we don't have to go into this spreadsheet and say from this station to this station and organize all that data. But what we do instead, and I'm not sure why this is, let's see. Is we take the sequence that it's telling us to use, and I kind of check at the bottom here. Okay, so this last one, 36 to 37 it's saying, but really there's no VPI down there, so we don't need this one here. And we don't need all this. So if I take all these sequences, I'm going to copy this order and enter that here for the upstream row count and downstream row count. See, it says copy and paste values and then formats to bring the colors over. So let's start with the values. That goes down to here. Now I'm going to paste the format, paste special formats, and that groups them together based on which way they're going, which way the ditches are going. Let me give this some kind of a border, and let's take out the rest. So now it's taking our, just with the ditch profile and the different VPIs, it is taking our that data and breaking it up, saying, okay, we're going from this station to this station, analyzing the ditch. The other thing, so that we haven't filled in the geometry. So this you would get off, I'm going to assume that it's most of the time we're going to have somewhat consistent geometry, I would say. So I'm going to assume we have 4:1 left and 4:1 right side slopes. This would have to be verified through the cross sections. So I would put something, what we are typically doing in here, and remember that we want to analyze, we don't want to go too crazy looking at these ditches if we can generalize some things. So if we can assume, like if some of the ditches are 6:1, that gives us more capacity. So that is, it's being conservative to say 4:1. And then if we looked and we saw it was not enough capacity and we look back, we could check, well, it's really 6:1, and we go back and adjust some things. Same with this depth. I'd say if we know in general we have 1 foot of depth, sometimes we have more. I want this to be not something that we get lost in the details of having to go through and check every single point, but something we can kind of scan through in general and say, okay, I know we have 1 foot of depth everywhere. We generally have 4:1 side slopes, and then we can start pinpointing the trouble areas in either our ditch capacity or our shear. So I'm gonna go ahead and drag these down. 4:1, 4:1, 0 bottom width, V ditch. Manning's in value of 0.035, something typical for grass. So it's going to, with that, it's going to calculate the max ditch capacity. Now the next step, and this hasn't been done, I'm going to delete these actual depths out. I'm going to put an actual depth of 1 to show that to make people assume that it hasn't been looked at yet. I'm just going to put 1. And drag that down. Okay, and that's the same thing we assume. But the step that we have not done is looked at each station of the ditch. And what I would do is look at each segment of the ditch. So that's why I had us color code it based on the direction it's going. And then we would use our drainage area maps in our drainage areas and our runoff computations to look for the flow. So say, let's just make up some flows here. Say our design flows are 5 CFS for these 4. And it's up to you how much detail you want to get into. If you want to say, okay, this whole green thing, say that's 1 drainage area, and here we approximate it's 2 CFS, and here it's 5, and here we're at the end of the drainage area, it's 10. So what that can do for you, now we have our actual ditch geometry in here. We have our max ditch depth, which is based on here, ditch depth that's available geometrically. And that is going to be, we see that, where do we see that? We see that here, the max depth. That's getting read from here. So say if I change this to 2, here's the max ditch depth. So that tells me that determines how much capacity this ditch could have. If it were flowing at that max depth with the same side slopes, geometries, longitudinal slope, that's how much it would have. But we've said that we have a design Q of 5 CFS in there. So how much actual depth would that be? So we would adjust the actual depth until the Manning's Q closely matches the Q of the design. So we're saying it's 5 CFS, so I would just come and play with this. And I'd say 0.5. And then Manning's Q is 1.8, so that's a little too low. 0.7, 4.4, 0.75, 5.3. Close enough. So match ditch capacity, so we're fine. And now the shear stress gets calculated, and it's saying 5.62 for that, and it's based on the actual depth and the slope and the unit weight of water. And we've selected a retardance class B vegetation. This is being looked up from where do I have this? Have this over here, this table, it's being looked up. You can modify the drop down if you're working on a project for a different client, but these are from the text.htm, the different lining types. So we have soil type B, and it's showing that it is okay as far as shear stress. It's okay as far as capacity. Now, if my Q were higher, if it were 50 CFS here, what kind of actual depth would I have to do to get 50 CFS? So we'd still probably work out with this. I could say 1.5, we have 33.9 CFS, 1.7, and we have 47, that's getting close, 1.72, 1.74, close enough. So that's 50 CFS, shear stress goes up, and it's still okay with this, because this has a 2.1 as the permissible shear stress. Look, if I change this, it changes based on what is in this table for that shear stress. So we've got retardants class E vegetation. It's looking up from retardants class E 0.35. So there it would say, if I actually changed it to, let me change it to something that will make it bad, like A. Okay, it was saying change the channel lining, so not good enough. Retardants class E is not good enough for shear stress. So if I make it B again, we're okay. And you can look up in the hydraulic design manual, and it's in the spreadsheet what the different retardants class vegetations are. Put that in the spreadsheet somewhere. Where did we put it? Here it is. So retardants class B, typical vegetation, Bermuda grass. C is crabgrass. D is Bermuda grass, common grass, good stand. So you can look at this information to see what you think you will have out there. When the shear stress starts getting too high, we usually go with a permanent soil retention blanket or some kind of riprap lining. So that's an example. It looks like in this case we're okay on ditch capacity. If we use that class E, we'd be okay on capacity. We're not okay on shear. So say I changed the flow. Say this was 200 CFS. Now my actual depth, what does it need to be 200 CFS? 2? Nope. 2.5. Notice it turns red. So we formatted the spreadsheet so when the actual depth goes above the depth that you actually have available, and therefore your Q, the Manning's Q, at actual depth is higher than the total capacity of the ditch, it turns red. In other words, that ditch does not have capacity. So you would have to look at changing the ditch profile or some kind of concrete lining to speed up the water and make it have more capacity, or taking the flow somewhere else. So we've tried to make this spreadsheet as user-friendly as possible to where you can look at the ditch you have, put an approximation of how much flow you will have at that specific station. I recommend looking through big swaths of the ditch and trying to break up your drainage areas according to this, and then just eyeballing between areas and saying, okay, this whole drainage area is 50 CFS, and this part of it is 90% of it, so it's 45 CFS, and this part is just half of it, so it's 25, and this part is barely any, it's only like 5 CFS. Don't kill yourself. Don't do 500 drainage areas to look at every station. And that's it. I think that sums up how to use this spreadsheet in a nutshell. If you have any questions, contact me, Eric Lisenby, or Delise Lockett, or Tamara Rodriguez. We are all familiar with this spreadsheet and can show you how to work it. All right, thank you.